Bismillah ar-Rahman ar-Rahim. We are going also to show you some examples related to the internal energy. If you remember, on the PV diagram, there was something called a PV diagram. And when a gas is in this state here, it has a pressure P, let's call it P initial, has a volume V initial, and has a temperature T initial. In this location, or in this state, there is an internal energy of the gas. I call it E internal. Okay, remember this. And that E internal was given by NCV T initial. Okay. If you go to another state here, let's say this is another state. This is initial final state. Also, it has a temperature. Let's call it T final here. And also, the gas has an internal energy in this state. I call it E internal also. So it's NCVT final, okay? All right? So as you go from one state to another state, the internal energy of the gas will change, okay? And CV, remember that CV has different values depending on a monatomic or atomic. So CV and CP for a monoatomic gas and diatomic gas. Remember, for CV is given by 3/2R, and this is 5/2R, and this was 5/2R, and this is 7/2R. This is like a review of what we have seen before in the previous videos. Let's look at this example here. Again, this is an exam problem. This example is taken from old exams. It says a 3-liter cylinder. That's the volume of my cylinder. 3 liter contains a diatomic ideal gas. So we are dealing here with ideal gas, where I can use PV equal nRT. Okay, at a pressure of 2 atmospheres. So he's giving you the volume of the gas and the pressure of the gas. What is the internal energy of the gas? So he's given you the pressure and the volume, and he wants the internal energy of the gas. This is a very simple example and straightforward. So if it is this is the internal energy of the gas. E internal is NCVT. Okay. So we know the number of moles. We don't know the number of moles, sorry, but we know the pressure and the volume. Okay. So we know, using the ideal gas law, PV equal nRT, so I can N times T. From this we can NT is actually PV over R. Okay, so I can use this instead of N here and this T here. I'm going to replace it by PV over R. So this will be PV over R times CV. Now this is a diatomic molecule. If we go to the diatomic molecule and look at CV, actually it's 5/2R. Okay, so this is PV over R times 5/2R. So R will cancel. So the answer here will be 5/2 times PV. Now let's be careful. We have, since this is internal energy, it's in joules. The pressure should be in Pascal, and the volume should be in meter cube. So you have to make some changes of units there. So this will be 5/2 times the pressure is 2 atmospheres. So 2 times 101 to the power 3. Now I'll change this into Pascal times the volume. The volume is 3 liters. That's 3 to the power minus 3. Okay, this cancels out. The 10 to the power 3 and 10 minus 3 will give you 1. And you have this 2 and this 2 will cancel out. You have 5 times 101 times 3, which gives you 1,500 joules. Around 1,500 joules. Okay, so that's the answer. That's the internal energy of the gas at this volume and this temperature. If we change somehow the volume, at this volume and this pressure, if somehow we change the volume of the pressure and the pressure of the gas, we go to another state, the internal energy will change because the temperature will change. Okay, thank you. Okay, let's look at this second example about the internal energy of an ideal gas. It says, again, this is an old exam problem. It says the temperature of 5 moles of an ideal monatomic gas. It's very important to know what type of gas is it, because CV and CP changes according to the type of gases we are dealing with. So this is monatomic gas. It means CV is 3 over 2R and CP is 5 over 2R. And there's one very important equation. It says CP minus CV is R. Okay, this is important. So the temperature is raised by 25 Kelvin. That's delta T. Okay, that's the temp. For example, it was 100, it became 125. It was 200, it became 225, and so on. So this is the change, the increase in temperature, delta T. In an adiabatic process, okay, I hope you still remember what is an adiabatic process. If you have some doubt and you forget, you just go back to previous videos and look at the adiabatic process. In the adiabatic process, the heat exchange is equal to 0 between heat exchange between the system and the environment. Our system, of course, is the ideal gas. Okay, so let me just quickly draw for you this. How does it looks like? You remember there was 2 isotherms. This is at T and this is at T plus delta T. And in our problem, delta T is 25 Kelvin. It has been raised. Now, so when is the initial? When is the final state? Before starting solving the problem, at least you should know that the initial is here and the final is here. Okay. So because the temperatures has increased and my adiabatic process will be something like this. It's a compression, okay? We know already that this is a compression and the work is going to be negative. If you find in your final result the work positive, it means you made a mistake somewhere. So you have to review your solution, okay? So we know that Q equal to 0 because we have adiabatic process. We know it's a monatomic gas. We are going to use the right value for CV and CP, and he's asking about the work. So we have where the work for adiabatic process is very well known because I'm going to use the equation which says that the internal is Q minus W. Okay, this is the work, the heat absorbed, and is the work done. Okay, and this the Q is equal to 0 here. Okay, because in adiabatic process, so the work from here automatically we can say the work is minus delta E internal. Again, another equation for delta E internal that you have seen before in previous videos. It says that delta E internal for is N CV delta T. Okay, and N CV delta T. Now CV is going to depend, is it a monatomic or diatomic gas? We look at the problem there. It says monatomic gas means CV is 3 over 2R. So I'm going to put this on this side. So the work will be, in this case, my work will be minus N CV delta T because it is minus delta internal, okay? So number of moles is not given, 5 moles is given here. Number of moles is 5 moles. CV is 3 over 2R because this is a monatomic gas, and delta T is 25 Kelvin right there. So this is equal minus, the minus sign. Remember, we said it's a compression, and when the compression happens, the volume decreases, and the work will be negative. So it is 5 times, this is 3 over 2 times R, which is 8.31, times delta T, which is equal to 25 Kelvin. Okay? If you do the calculation correctly here, you get minus 1,558 joules. That's the work in this work done by the gas. The work done by the gas in this process. Because the work done on the gas because it's a compression. When you have a compression, it's an external work. The gas is compressed. So this is the work done on the gas. The minus sign here. Okay. And this is also equal to the minus the change. If he asks you to find, for example, so this is the end of the question. If he asks you to find the change in internal energy of the gas, you take this value here with a positive because the work and delta internal are related by the minus sign here. So delta internal in this problem, if he asks about the change in internal energy, it will be plus 1,558 joules. If he asks about the change in internal energy. So the work and the internal energy are equal in magnitude, but there's a minus sign between the two. Thank you. Okay, let's look at this example number 3 here. This is related again to the internal energy, heat and work and so on for ideal gas. So here it says we have a PV diagram as you can see, and we have 3 moles. So number of moles in this problem is 3. Of an ideal diatomic gas. So we are highlighting the word diatomic because we want to know which value of which expression for CP or CV will take. The gas is taken through the cycle A, C, B, and A. You can see it here. A, C, B, and A, okay? So you remember that this is a counterclockwise cycle. And let's say, if we use this expression, it's a counterclockwise cycle. He's giving you the temperature at different locations here, or different, at this, at state A, temperature is 300 Kelvin. That's the lowest temperature. At B is 600 Kelvin, and C it is 492. And he's telling you that this is an adiabatic process here. Adiabatic process. So he's asking you about the network done, the network for the cycle, okay? So the work, it will be the area enclosed here. And if you remember from previous videos, when you have a counterclockwise cycle like this, the network will be negative. So make sure that your work at the end should have a minus sign. If it is positive, then there is a mistake, and then you have to review your work, okay? So, there are many ways to solve this problem. I'm going to solve it in such a way to emphasize the heat for ideal gas laws, okay? We have to use, first of all, this is a cyclic process, okay? Cyclic process. And for cyclic process, we know that delta E internal, which is equal to Q net minus W net, is equal to 0. Because remember what is delta E internal? It's NCV delta T. For cyclic process, delta T is 0, and therefore you end up with delta E internal for the cycle, not for each process, for the cycle, for the whole cycle. So it means that in this case, the work net, W net, is equal to Q net. So I'm going to calculate Q net because I have one of the Q's is 0. It will make my life very easy because I will have to calculate only two Q's. Q for this process and Q for this process, because his Q is already 0. So this Q net will be equal to Q AC, okay, plus Q CB plus Q BA. Okay, that's how you, and this is 0 already. Yeah. Now, if you forget this these expressions, you have to go to the videos and look when we were doing the theory and explaining the concepts. You have to go and review them. Okay. For AC process A to C, we have a constant pressure. We call this heat NCP delta T, which is the specific heat ratio, the specific heat, molar specific heat at constant pressure, because the pressure is constant in this process here, okay? And here, we call this NCV delta T, where the volume is constant, okay? When the volume is constant, we put CV for the heat, okay? Remember, for a constant pressure process, this one here is N, number of moles, Cp, which is a molar specific heat at constant pressure, delta T, the change in temperature between these two states, okay? And here it sends Cv delta T. So let's put the numbers here. We know that this is a diatomic molecule, so my Cp is actually 7 over 2R. So I have N 7 over 2R. Then I put the temperature. I'm going from A to C, so I have to put Tc minus Ta, and this will be positive, of course, because Tc is greater than Ta. And here I have to put number of moles 5 over 2R. Then it will be Ta minus Tb. Okay, let's put the numbers now. Okay, let's put the numbers. Number of moles is 3 moles. You can see it here. So it will be 3 times 7 over 2 times 8.31 times Tc, which is 492, minus 300, that's 192 Kelvin, okay? And here, and this one here will be 3 times 5 over 2 times 8.31 Ta minus Tb, which is minus 300, okay? If you do the calculation, you have to add these two terms. This is 0 here. If you do the calculation correctly, then you get the minus 1,945. Minus 1,945 joules. And that's the work net. We are looking for this work net, okay? This is the answer here. And I told you, my son, be careful. Your work will be negative because it is actually the area enclosed in this cycle, and it is counterclockwise. So you expect the work to be negative. You can see it here. It's minus 1,940, and this also equal to Q net, by the way. So Q net equal W net in this specific problem where you have a cyclic problem. It's a cycle, so your delta internal is 0. Thank you. This is another example related to cyclic process, but remember, be careful here. My son, I will show you something about this PV diagram. It says in the PV diagram shown here, you can see it here also here. If you are not able to read these numbers here, so they are here. This is the volume at two different states, A and C, and this is the pressure at these states, B and D and A, C here, okay? So it says that in the PV diagram shown, 150 joules of heat is added to the system, which is our gas, in the process A, B. So during the process A to B, the red process here, 600 joules is added to the system, so it's positive. So I have Q AB is equal plus 600 joules, okay? And I know that the equation for this process, since the volume is constant, this is N CV delta T, okay? That's very well known. Then I have the AB, okay, sorry, 150 joules. You can see it here, 150. 600 is for the process B to D, okay? 150 joules, okay? This doesn't change, it's the same, because we have constant volume. And we have, and we have Q, B to D is equal to 600 joules, and plus, it's also added to the system, okay, plus 600 joules, and I know this is NCP delta T. Be careful, delta T here and here are not the same, because they are different temperature changes here, okay? Then he is asking about the heat added in the process ACD. So he wants Q, A, C, D. A, C, D. Look here, my son, this is not a cyclic process. I'm going from A to D to two different paths. And remember that heat is path dependent. Don't expect this heat to be equal to this heat here, okay? Do not expect that. But let's do the calculation and see that it is not, because the heat to go from here to here is actually 750. The heat to go from here to here is not going to be 750 because the heat is path dependent. And he's asking about this heat here. Of course, this is QAC plus QCD, okay? QAC plus QCD. All right? So this QAC is actually equal, but there are two ways to solve this problem, by the way. I'm going to solve it using two different techniques, okay? Just to give you an idea about, you can solve physical problem with different approach, okay? So the approach I'm going to use the cyclic approach, okay? I'm going to go from A, B, D, C to A, okay? So if I'm going to say that delta E internal for the cycle, okay, is equal to 0. We know that. So this is Q net. Q net if you go through this path here, okay? It will be Q AB plus Q B D plus Q D C plus Q CA. You agree with me? Minus work net, W net, which is equal to the area under the curve, okay? All right? I'm sure anybody in this, any one of you can calculate the area which is enclosed in this cycle here, because I'm talking about cycle here, okay? And that area actually, I can calculate directly how much is that area. It is here. It will be this times this, okay? In meter cube. So this is 0.003. 0.003 times this one here, which is 50. Be careful, it is in kilopascal, all right? So this will give me 150 joules, and it is positive. Do you know why it is positive? Because I'm going clockwise. As I'm going clockwise, my work is positive. That's the work to go from A, B, D, C, and A, okay? Now, let's go to the heat now. I'm looking for, this is given to you from A to B. It's 150 joules. And this is also given to you, right? It's plus 600 joules. So I can calculate this heat. I can calculate Q dC plus Q Ca, which is equal to 150. And I take this to the other side, minus 600. And I take this to the other side, minus 150 joules. It gives me minus 600 joules. These two will cancel. You agree or not? You agree with me? So this is actually, which heat is this? Q D C A. But I'm looking for what? I'm looking for Q A D A C D. I'm looking for the opposite. I'm looking for this Q, not this Q here. So Q A C D is equal minus Q D C A. This is important to know, my son. Q A C D is minus Q D C A. And I know this Q D C A is here. So it will be minus 600 joules, which is equal to what? Plus 600 joules. Okay? So that's the final answer. This is the answer to this question here. Okay? And as I told you, this heat is different from the sum of these two heats, which is 750. Okay? So this is the answer to the question. I'm going to try now to solve it the other way by using the other technique, which is, so this is done. Let's look at the other way to solve the problem. So I'm going to calculate QAC. And I know what is QAC. QAC is constant pressure, so it will be NCP delta T. Okay? But I don't know CP in this problem because it doesn't mention what kind of ideal gas. Is it monatomic or diatomic? But I have some information here which will help me find CP and CV, okay? For example, I can go to this equation here, okay, and calculate CP. Let's calculate CP from here, okay? From this equation here, from this information here, okay? So what is CP? CP is what? Is QBD over N delta T. How much is QBD? It's 600 divided by N. Of course, it didn't give you a number of moles, but delta T, since we are working in constant pressure, this is P delta V over NR. So N will cancel. R will go up, okay? So it will be 8.31 times 600 divided by the pressure. What is the pressure for this, for AB? For BD here. What is the pressure here? It's 80, yeah? I'm working in BD here. So it's 80 to the power 3. That's 80 kilopascal. Times delta V, the change in volume between B and D, that's 0.003. That's 0.005 minus. If you do the calculation here, you find that CP is 20.8. 20.8 joules, of course, with mole Kelvin, okay? That's the units for CP. I can take now this CP here and plug it here to find QAC, okay? So, now, so CP, okay? So what is my value for delta T in that case, for AC? For AC, how much is delta T? So I have N, and delta T is what? Is P delta V over NR. So I'm going to cancel the N because I don't need the N, okay? And CP is 20.8, 20.8 divided by 8.31, that's R, times the pressure here is 30 and to the power 3 times delta V between these 2 points, it's 0.03, and that's it. And you do the calculation here, and you find that QAC will be 225 joules. 225 joules, and it is positive, okay? That's QAC. Now let's calculate QCD, because he's asking about QACD, which is QAC plus QCD. So I'm going to calculate QCD now here, and add both of them, okay? Add them. So QCD will be what? N what? CD. Huh? It's constant volume. It will be NCV delta T. But I don't know CV, but I know the relationship between CP and CV, right? If I found CP, I can find CV by what? CP minus R will give me CV, okay? So CV on the side here, we can write it here. CV will be CP minus R, which is 20.8 minus 8.31, which give you 12.7 joules per mole Kelvin. Okay? 12.7 joules per mole Kelvin. Or 12.47. Let's write 12.5, okay? Joules per mole Kelvin. Okay? So I know CV there, huh? And I'm going to use N. CV is here. Delta T is what? I'm working here as constant volume, so it will be V delta P over NR. Number of moles also cancels here. Huh? So let's put the numbers now and do the calculations. So CV is here 12.5 times the volume for this process is 0.005 times the change in pressure for this process, which is 80 minus 30, which is 50 10 to the power minus 3, divided by 8.31. If you do the calculation correctly, you will find 375 joules with a positive number. That's the heat for this process here. And this is the heat here. This is the heat for the first process, which is A to C. Now, how do you find the heat for the whole process A, C, D? You add the two numbers, right? If you add, so Q, A, C, D will be 225 plus 373, which will 75, which will give you exactly 600 joules, the same value that you have found in the previous the previous method here. So this is a complete problem on using the heat for different processes and using the internal energy for a cyclic process and so on. Thank you.